Hello everyone. Welcome to another episode of Deep Dive Knowledge. Hello. I'm excited to discuss your study on manifold learning and evaluating manifold learning methods. Could you please start by giving me an overview of what manifold learning is and why it is important in data science?
Hello. I'm glad to hear that you're interested in the study on manifold learning. Manifold learning is a technique used in data science to uncover the underlying structure within high-dimensional data. In our context, a manifold refers to an approximate restudy of the relationships between data points in a high-dimensional space. It helps us understand how these data points are related to each other, both locally and globally. The importance of manifold learning lies in the fact that in many real-world datasets, the true structure or relationships between data points are not known in advance. By applying manifold learning techniques, we can gain insights into the hidden structure and patterns within the data, which can be crucial for various data science tasks such as clustering, classification, dimensionality reduction, and visualization. Manifold learning algorithms aim to map the high-dimensional data into a lower-dimensional space, while preserving the important relationships between the data points. This lower-dimensional restudy, or embedding, allows us to better understand and analyze the data, as well as make more informed decisions in subsequent machine learning pipelines. Overall, manifold learning is an important tool in data science as it helps us uncover the hidden structure within high-dimensional datasets, leading to improved data analysis, decision-making, and ultimately better machine learning models.
Thank you for the insightful overview of manifold learning and its importance in data science. It seems that manifold learning can greatly aid in understanding complex datasets by uncovering the underlying structure and relationships between data points. Could you please explain some of the specific techniques that are commonly used in manifold learning?
Certainly. In manifold learning, there are several techniques commonly used to learn the underlying structure of high-dimensional data and create lower-dimensional restudies. Here are 4 popular techniques. 1. Principal Component Analysis, PCA. PCA is a linear dimensionality reduction technique that aims to find the directions of maximum variance in the data. It identifies the principal components, which are orthogonal to each other and capture the most significant information in the data. By projecting the data onto a subset of the principal components, PCA can reduce the dimensionality while preserving the overall structure of the data. 2. Locally linear embedding, LLE. LLE is a nonlinear technique that assumes that the data lie on a low-dimensional manifold within the high-dimensional space. It works by reconstructing each data point as a linear combination of its neighboring data points. LLE seeks to find a lower-dimensional restudy that preserves the local relationships between the data points. It aims to minimize the reconstruction error and uncover the underlying manifold structure. 3. T-distributed stochastic neighbor embedding, TSNE. TSNE is a nonlinear technique that is particularly effective for visualizing high-dimensional data in 2 or 3 dimensions. It models the similarity between data points in the high-dimensional space and maps it to a similar probability distribution in the lower-dimensional space. By minimizing the divergence between the 2 distributions, TSNE can create a compact and meaningful restudy of the data, emphasizing the local structure. 4. Isometric Feature Mapping, ISOMAP. ISOMAP is another nonlinear embedding method that assumes the data points are connected in a neighborhood graph, where the distances between the nodes are geodesic distances. It applies multidimensional scaling, MDS, to find a lower dimensional restudy that preserves the pairwise distances between the nodes as much as possible. ISOMAP is powerful because it takes into account the global structure of the data and can uncover curved manifolds. These techniques offer different approaches to capturing the underlying structure within high-dimensional data and provide insights into the relationships between data points. It's important to select the appropriate technique based on the characteristics of your data and the specific goals of your analysis.
Thank you for providing an overview of the 4 popular manifold learning techniques. Principal Component Analysis, PCA, Locally Linear Embedding, LLE, T-Distributed Stochastic Neighbor Embedding, TSNE, and Isometric Feature Mapping, ISOMAP. It's interesting to see that these techniques vary in their linearity assumptions and their ability to preserve local versus global relationships. Now, the study also mentions the concept of noise injection for evaluating the performance of manifold learning techniques. Could you explain how noise injection works and why it is an important evaluation method in manifold learning?
Noise injection is a technique used to better understand the underlying structure within high-dimensional data when applying manifold learning methods. It involves generating surrogate datasets by adding Gaussian noise to the original dataset. The variance of the noise can be scaled for each subsequent surrogate dataset. The purpose of noise injection is to observe how different manifold learning techniques perform when subjected to noise. By comparing the noise-injected embeddings to the embedding of the original space without synthetic additive noise, we can evaluate the performance of each technique. The noise-injected embeddings and the original embedding are compared using Procrustes analysis. Procrustes analysis is a statistical method that measures the similarity between two shapes. In this case, it rotates, scales, and translates one embedding onto another to minimize the sum of squared differences between each data point. The resulting difference is a measure of similarity, which can be analyzed to observe how each embedding method performs when subjected to noise. The change in the Procrustes distance, which is the measure of similarity, is then plotted relative to the scale of the synthetic additional noise. This allows us to draw conclusions about the performance of each manifold learning technique. Noise injection is an important evaluation method in manifold learning because it helps us understand how different techniques handle noise and potential future data drift. It provides insights into the generalization of the resultant embedding and how it may respond to noise. By evaluating the performance of manifold learning techniques under noise, we can make more informed decisions on how to preprocess or handle the data before passing it on to subsequent machine learning pipelines. Additionally, noise injection can be used as a way to expand upon the process of performing exploratory data analysis, enabling us to deepen our understanding of the hidden, obscured structure in any high-dimensional dataset.
Thank you for the detailed explanation of noise injection in evaluating manifold learning techniques. It's fascinating to see how noise injection allows us to assess the performance and generalization of manifold learning methods in the presence of noise. This evaluation method not only provides insights into the robustness of the techniques but also helps in making informed decisions regarding data pre-processing and subsequent machine learning pipelines. In the study, you mentioned that examples in Python are provided to illustrate the analysis. Could you briefly explain how these examples were implemented and how they contribute to understanding manifold learning and evaluation methods?
In the study on manifold learning and evaluation methods, the examples in Python were implemented to demonstrate a practical application of the noise injection analytical approach for evaluating manifolds. The implementation process involved the following steps. 1. Generating surrogate datasets. Gaussian noise was added to the original dataset to create surrogate datasets. The variance of the noise was scaled for each subsequent surrogate. 2. Embedding the datasets. The generated surrogate datasets were then embedded using a selection of manifold learning techniques. This involved mapping the high-dimensional data to a lower-dimensional space while preserving the underlying structure. 3. Comparing the embeddings. Procrustes analysis, a statistical method for comparing two shapes, was used to compare the noise-injected embeddings with the embedding of the original space without synthetic noise. This analysis involved rotating, scaling, and translating one space onto another to minimize the sum of squared differences between each data point. The resulting difference provided a measure of similarity and was used to evaluate how each embedding method performed when subjected to noise. 4. Plotting the results. The change in the Procrustes distance, a measure of similarity, was plotted relative to the scale of the synthetic additional noise. This allowed for a visual restudy of the performance of each technique in the presence of noise. These Python examples contribute to understanding manifold learning by providing a practical demonstration of how different techniques perform in the presence of noise. By comparing the performance of various embedding methods, researchers and practitioners can gain insights into the robustness and effectiveness of each technique. This understanding can help in selecting the most suitable manifold learning method for a given dataset, taking into account the level of noise and the desired accuracy of the embedding.
Thank you for explaining the implementation process of the Python examples and how they contribute to understanding manifold learning and evaluation methods. It's valuable to see how these examples provide a practical demonstration of evaluating manifold learning techniques in the presence of noise. This allows researchers and practitioners to gain insights into the robustness and effectiveness of different techniques and make informed decisions about which method to use based on the specific dataset and noise level. The visual restudies of the results further enhance the understanding of the performance of each technique.